So in this episode, we are going to cover what happens after a switch is thrown in an RC circuit. We're going to look at the transient period, and we're going to do some calculations about how to find the voltage at any, for a resistor or for a capacitor at any point in time, in relation to what the time constant is for the circuit. So some of those terms are new, so let's go ahead and get into this. So we'll start here with just a generic RC circuit, and we call it an RC circuit obviously because there's a resistor and a capacitor. Now we're introducing the idea of a switch turning on and off because that's going to make a difference. If it's just purely resistive, then a switch being thrown is still going to get an instantaneous response from the resistors because if you change the voltage instantaneously, you change the current instantaneously on a resistor. But as we know, with a capacitor, it does not change voltage quickly. It has to build up charge on one of the plates. So, we have to look at what is time zero because that's when our count starts. So, now we're going to start to look at, what happens before the switch is thrown. So here we're noting that this is an uncharged capacitor. So there's no voltage on this initially. So when we throw this switch, as we discussed in the previous lecture, all the voltage is going to be on the resistor because it takes time for those electrons to move around and combine on this bottom plate. So, however long that takes, there's a specific amount of time it takes, right? And it's in relation to the R and the C. We're going to multiply those together here shortly with our tau calculation. But that, the bigger the resistor, the bigger the capacitor, then the bigger the time constant, which means it's going to take longer for it to store that energy in that electric field. So this is what it looks like before the switch is thrown. So this is, if you've done physics before, sometimes t equals 0 minus. So this is that period of time before actual t equals 0 when the switch is going to make contact here. All right. So there's no voltage on the capacitor, there's no current, and there's no current because there's no voltage on the resistor because remember V equals I times R. So now we throw the switch. We are at time equals 0. So it's the instant that those contacts make a connection here. So, here we've got, we have an uncharged capacitor because initially it was at 0. So at the instant these contacts make a connection, again, all the voltage is on the resistor. So all 10 volts is on the resistor. None of it is on the capacitor because we have not started to build up a charge and therefore a potential across the component. And so we are at what I call max current because initially all the voltage is on the resistor and that's the most current you're going to get. Once, time ticks on, this is going to store up charge. There's going to be a smaller voltage drop across the resistor and you're going to get a smaller current. So it starts out at max current and then it decays down to 0. Same thing with the voltage on the resistor. It's going to decay down to 0. So the capacitor is the one that's in the growth mode because it's going to start at 0 and it's going to end up at 10 volts because eventually it's going to equal the voltage of the source. And no voltage will be across the resistor. And because there's no voltage on the resistor, that means we have no current. Okay? So that's the general process. So initially uncharged, everything is at 0. The moment the contacts make a connection, all the voltage is on the resistor, we're at max current. And then once we get to what we call steady state after the transient period, then we have no current and we have no voltage on the resistor and 10 volts on the capacitor. Okay, so that's the operation. Now let's see about how long it takes for that to happen. So we do that with the time constant tau. That's a Greek letter tau. So the time constant is just resistance times capacitance, and that's the total resistance and total capacitance in the circuit. So it says the bigger the capacitor, the more time to charge to a given voltage with a given current. So the bigger the resistance, the smaller the current, so the more time to charge. Okay, so both of those things fight against how quickly it's being done. But sometimes you want a big RC time constant because you don't want it to charge too quickly. So it just depends on what you're doing. So here's another key thing about the time constant. It takes approximately 5 time constants to charge or discharge a capacitor to 99.3% of its steady state value. And that 99.3% isn't just a random value. That's a calculation from exponential functions. Okay, so we're actually going to start using some exponential functions here, some growth and decay functions to describe what's happening with the voltages and the current. Okay. All right. So I actually have an equation that's on the board for this, and it looks a little bit different than what you see here. So where you see E over R, well, that's for the current, but for the voltage here, where you see E, that's just the source voltage. I write that as V sub S. So when we go to the board, it's going to look a little bit different than what you see here, but it's the same concept, okay? So if we're going to talk about growth and decay functions, remember, it's always, if I wanted to find the instantaneous voltage of this resistor, and I've got, in this case, it's a decay function because I'm times e to the negative t over tau, okay? I is also a decay function because it's times e to the negative t over tau, but the voltage on the capacitor is the growth function because it's 1 minus e. So if you get rid of the e's on here and you just use the two, e to the negative t over tau, that is a decay function just by itself. And then 1 minus e to the negative t over tau, that is a growth function. Okay, so that's just a base, exponential growth and decay. E to the negative x and 1 minus e to the negative x. And these are, that's just with an amplitude of 1 in each case. But you can see here, it has sort of a big rounded corner, but in both cases, it does not cross whatever it's approaching. Okay, so a decay function, wherever it starts from, always decays down towards 0, and a growth function is always approaching some other level. And those levels, whether you're decaying to 0 or 1, we call that an asymptote. So you learned about that back in, I think, Algebra 2. So here's the generic, or I would say the general format of a decay or a growth function. So you start out like in a decay function here, 63% of that value, so whatever this is here, if you subtract 63% from there, that's your next value at time constant 1, okay? At time constant 2, from this point to 0, take 63% of that and subtract it, and then here's your new value. Okay, and this is why it's in an asymptote, because it's going to get incredibly close, virtually the same line. But if you were to look at this microscopically and keep and had the ability to keep zooming in out towards infinity, they would get very, very, very close to each other, but they would never actually touch. Right? That's the definition of a asymptote. So It's just an algorithm over and over. 63% of what is left. It's not 63% and 63%, because then that would be 126%. So we're saying 63% of what is left, subtract that, that's your next value. From this time constant, take 63% of that, that's what your next value is. And so you just keep doing this until you get smaller and smaller deviations until it flattens out. Same thing with the growth. Wherever you're at, where you're growing to, we're going to add 63%, and that's your first time constant. Then from this position, not from down here, because again, you'd be at 126% up here. From this position to this level, 63% of that, come over. Whatever's left here, 63% of that, 63%, all the way until you start to flatten out the curve here. Okay, so that's why we say 63%. Here's an example. So we have a 20 volt source, we have a 1 kilo ohm resistor, and a 1 microfarad capacitor, which gives us a time constant. If we take kilo times micro, that gives us milli. So this is a 1 millisecond tau. Okay, so that would be 1 millisecond here. The initial voltage of the capacitor is going to be 0. The initial value of the voltage on the resistor is going to be will be 10. I'm sorry, 20, because that's the total voltage of the source. And then initially it's going to be 20 volts minus I'm sorry, 20 volts divided by 1K, which will give us 20 milliamps. So that's going to be the max current. And then at steady state, the voltage on the resistor is going to go to 0. The voltage on the capacitor is going to go to 20. And the current will be at 0. Okay? So that's initial values and final values. And these subscripts here, init, that's initial, and then SS is steady state. Okay, so the voltage on the cap is going to be 20 volts times, I'm just going to erase all this here, 20 volts times 1 minus e to the negative t over tau. Okay, and this will have an in parentheses over here that it's trying to leave in this format, but you get the idea, right? So this is going to be a big parentheses on the end here. Okay, so for the this is going to be 20 milliamps, and that's times just the decay function of t divided by tau. Okay, this one is 20 volts times that. Okay, and if you wanted to know the voltage on the resistor, instead of 20 milliamps here, you would just trade it out for 20 volts. Okay, so again, this is the growth function, 1 minus e to the negative x, and then this is the decay function, e to the negative x, which, you know, for us, x is this calculation here. Okay. So just a couple examples here. Again, 1 kilo and 1 micro is going to give you 1 milli. If you have 2 resistors in the circuit, those add up to 3K, and this is a series circuit, so that's kind of important. So this one is in series with this one, so we have 3K, and then 3K times 47 pico. We can do that. So 3E3 times 47 E negative 12, because pico is 12, right? So that gives us 141. That is nanoseconds. Okay. Now what about this? Remember, these are in series with each other. Okay. So when you have capacitors that are in series, you treat them like resistors in parallel. Okay. So in this case, we're going to have a total resistance of 3K ohm, and we're going to multiply that times 100 in parallel with 100 gives you 50. So that's 50 picofarad. So that's going to give us, if we take 3E3 times 50E, and that's, yeah, 50E12. And we get 150 nanoseconds. Okay. All right. So I think it's time to go ahead and do some of these on the board. And we'll look at a couple of different circuits. We'll start out with just a straight RC, and then we will take it up a little bit. Okay, so here is the way that I would write these equations. Okay, and so I've got the voltage on C, on the capacitor, is the source times 1 minus e to the negative t over tau, where in all cases tau is r times c. V sub r is the source times the decay function of e to the negative t over tau, and then I equals I max times e to the negative t over tau. Both of these are decay. This one is a growth. I max is Vs over R, or RT, if you have a total resistance to look at. Okay, so that's what we're going to be using in our calculations here. So let me just start with a basic RC circuit. And in this case, we now have 2 resistors here, and we still have another capacitor in series with them. So now when I go to do my tau, R times C, what I really mean is the total resistance times C. And so that's 1.2K plus 6.8K, which will give us 8K ohms total, right? So that means that tau equals 8 kilo ohms times 47 micro. And that gives me 376 milliseconds. So tau equals 376 milliseconds. Okay. So now we can have our equations. So let's look at t equals 200 milliseconds. And then let's also look at t equals, let's do 1 microsecond. How about that? So 4 tau would be somewhere around 1.2 micro. So this is just under 4 tau. Okay. So the first one we're going to look at is t equals 200 milliseconds. So the voltage on the cap at 200 milli is 9 volts times 1 minus, remember this is a growth function, 1 minus e to the negative 200 milli divided by 376 milli. So 9 times 1 minus e to the negative 200 divided by 376. And I get 3.71 volts. Okay? So now the voltage on the resistor at 200. So now this is just times, it's decay, so times e to the negative 200 over 376. So hopefully this adds up to 9. And it does 5.29 volts. Is that right? Is that 3? Yeah, that's 9. That's right. Okay. Now the max current, and this is going to be for both problems, so I'm going to put the Imax up here after I'm done. So that's going to be 9 volts divided by 8K. .13 milli. Not a lot of current. Okay, so we want to find I of 200 milliseconds. So here we've got 1.13 milliamps times e to the negative 200 milli over 376 milli. And that is 664 microamps. Okay. So we had 3.71 volts, 5.29 volts, and 664 microamps. So this is 200 milliseconds, and this is VC, VR, and I. Okay. All right, so I'm going to go ahead and get rid of this stuff over here. I've got the two things I need up there. The other one was, this was 1 microsecond that we're going to look at now. So if I was constructing a table of these values, this is kind of how it would look. You may notice the format from the exams, quizzes you already taken. So now we're going to look at 1 microsecond. Okay. So the voltage on the cap at 1 micro is 9 volts times 1 minus e to the negative 1 micro over and that is a micro over 376 milliseconds. And so there I get 24.0 micro. Wait a minute. Multiply times. So I didn't want to do 1 microsecond, did I? Because that's lower. I want to do 1 whole second. What was I thinking? So this is 1 second. 1 microsecond is super, super quick. I was wondering why I'm down here in the microvolts. So we want 1 second. So that changes things here. And now I get 8.37. That's much more reasonable. So now the voltage on the resistor at 1 second is 9 volts times it's just 9 volts times e to the negative 1 second over 376 milliseconds. So this is going to be millivolts, 630 of them. Okay, and then, so we have our Imax already, so I of 1 second is 1.13 milliamps. This is going to be super small. Times e to the negative 1 second over 376 milliseconds. 79.1. And that is microamps. Okay, so 8.37, 630 millivolts, and 79.1 microamps. Okay, well, let's go ahead and add another capacitor and see how that goes. And so here is the next circuit. So now this time we've got a couple of these that are in parallel together. They're going to combine to give us, actually going to give us 5.5 micro, because when they're in parallel like this, we can treat them like a single series resistor. So if we add those two together, really the circuit that we're analyzing sort of looks like this if you redraw it. If you just want a single resistor and a single capacitor here, there's 5K ohms total, and then these add together to give you 5.5 micro. Okay. So the time constant, tau is going to be R times C, and this is R total times capacitance total because there's 2 of each. So we've got 5K times 5.5 micro. And we get 27.5 milliseconds. Okay, I can get rid of this. And I'm going to keep these two values. So RT is 5K, and the capacitor total was 5.5 micro. Okay. So if that is the tau, then let's go ahead and look at T equals 30 milli. And then how about 100 milli? Okay. So now the voltage on the cap at 30 milliseconds is going to be 10 volts times 1 minus e to the negative 30 milli over 27.5 milli. So 10 times the quantity 1 minus e to the negative 30 divided by 27.5. 6.64 volts. Voltage on the resistor at 30 milliseconds. Because remember, this is the total voltage on, that both of them share, and this is the total, well, they're parallel here, but they will both have the same voltage drop here. So the voltage of R, so that's going to be 10 times e to the negative 30 over 27.5 milli. And that gives us 3.36 volts. The maximum current is 10 volts divided by 5K, because that's the total resistance in the circuit. So that's nice. It gives us 2 milliamps. So that's our max current. So then let me see, I max is 2 milli. Okay. So now I of 30 milliseconds is 2 milliamps times e to the negative 30 milli divided by 27.5. And I get 672 microamps. Okay, so the voltage on the cap, the voltage on the resistor, and the current. And we've got, this is T equals 30 milliseconds, and we're also looking at T equals 100. So this one's 6.64 volts, 3.36 volts, and the current here was 672 micro. Okay. So you can see here, we're just above 63% because we used 10 again. So we're just above 63%. We're just above our time constant. Okay. Now this one is going to be over 3, almost 4. So the majority is going to be here, very little here, almost nothing here. So let's go ahead and do the next one. So the voltage of the capacitor at 100 milliseconds is 10 times 1 minus e to the negative 100 milli over 27.5 milli. .74 volts. So there you can see 97.4% of the way there. And then the voltage of the resistor is at 100 milliseconds is 10 times e to the negative 100 milli over 27.5 milli. And that gives us 264 milli volts. 264 millivolts. Not going to be much current left for that. So I of 100 milliseconds is the maximum we were going to get was 2 milli, right? So times e to the negative 100 milli over 27.5 milliseconds. And that gives us 52.7 microamps. So you can see here, start off, capacitor takes 63% of the voltage at 1 tau, which was 27.5. We looked at 30, so it was just past there, and then we looked at 100, which was almost to 4 tau, and you can see that everything has started to settle in. Okay, and remember, 5 tau takes this to 99.3%. Okay, all right. Thanks for stopping by the lecture.